Okay, I think there's a 1 or 2 minutes or second delay on this, so now I'll start talking. Welcome back, everybody. Thank you for joining us. We're back today talking about teaching reproducibility and replicability in spatial data science. We have a great team of 3 organizing this session, and I'll pass it over to them to take over. Thanks very much.
Great. Yeah. Thank you, Grant. Hello, everyone. Thanks for joining the session today. We're really excited to talk to you guys about teaching R&R in the GI sciences and spatial data science, kind of in geography writ large. And we've kind of hopefully got a really nice program for you, but I thought maybe we start out with doing some introductions. So my name is Peter Kedron. I'm an associate professor of geography at UC Santa Barbara, and I'm also an associate director of the Center for Spatial Studies and Data Science. Let me quickly apologize. My camera's a little bit dicey this morning for some reason, but we won't let that slow us down as we go through this presentation because you'll mainly be seeing the slides anyway. I'll pass it off to Joe to introduce himself and then on to Andrew.
Yeah, thanks. I'm Dr. Joseph Holler, associate professor in the Department of Geography at Middlebury College. And I'll pass it off to Andrew.
And I'm Andrew Trgovac. I am a teaching assistant professor in the School of Geographical Sciences and Urban Planning, and I'm also our department's GIS coordinator. So we wanted to talk a little bit about what you're going to be learning first off as far as the workshop and our general agenda. So we're going to start off by giving you a basic introduction into R&R and what we think about R&R as far as in education and in our classrooms, and then what you can take away from this workshop. We're going to then transition into talking about the competency rubric and how R&R fits into that. And we think it's extremely important to have breaks in between so that we can have discussions. So we're going to have a Q&A after that. If you have any questions, please put them in the chat. We'll address them. And if you need to upvote them, we would appreciate that. If there's some question or comment that you think is really interesting and should be addressed, please upvote on that. And then we'll get into the meat of the entire workshop with the classroom model where we use R&R in the classroom itself, link that to project-based learning, and then go through the implementation of R&R in the classroom using techniques that have been done in various classrooms at multiple universities. Again, more Q&A, and then what are the next steps that are going to be coming up for R&R, and then give you a bunch of resources where you can then take these techniques and put them into your classroom.
Thanks, Andrew. So this isn't our first workshop for this conference series. We did this last fall as well and gave a little survey at the beginning just to ask the audience which open science practices folks were already aware of and which ones they were interested in starting to use more and which ones I hadn't even really heard of before. And the graph sort of sorts them as to the most commonly aware open science practices on the left and the least commonly aware or least acknowledged in the geographic and spatial data science community on the right. And just at a glance, you can see that we all kind of know that we should be using open source software and sharing our data and sharing our code. But when it comes down to the finer details and deeper, more meaningful practices in open science, our community in spatial data science is not so aware. And so what we're really trying to do overall is move ourselves and our students towards the left side of the graph and sort of allow these practices to start permeating throughout our field and influencing the way that we kind of generate and validate knowledge in our discipline.
Yeah, thanks, Joe. So I guess everyone settle in because you're going to get me for a little bit of time now. But to start out with this, I think we just want to make sure we set the stage as usual with sort of understanding what we mean with some key terms here, right? So I think often when we talk about reproducibility, replicability, particularly in the data sciences, spatial data science and otherwise, we tend to focus in on the computational reproducibility sort of definition, which really indexes in on sharing sort of this third and fifth columns here, sharing data and sharing code or procedures, usually in the form of code. And when we talk about reproduction, if you're using the National Academy of Sciences reports from a few years back, computational reproducibility really focuses on having the same data in the same code and getting the same results. And the replication there, we get some variation in the data, usually with similar procedures or similar code, and we're looking for a comparison of similarity of results. And that's a really nice way to start thinking about reproducibility and replicability. But one of the things that we really want to emphasize and bring forward in this particular workshop, and kind of as we talk about this as a field writ large, but particularly in focusing on education and pedagogy, is that these practices serve a much larger epistemological purpose within the field of geography. So, Joe, can you bounce back real quick for a second? So just really quickly on that, as we think about reproduction and replication, we're thinking about these as forms of internal and external validity checks, right? They serve this larger purpose beyond just sharing data and code. Certainly that reusability aspect is important, but this validity check aspect, the role they play in moving forward our knowledge is really important. And then, yeah, pop ahead, Joe. Thanks. And so if you think about that sort of holistically, we've been thinking about it in terms of this idea of a veridical data, a spatial data science. And this is riffing on an idea that's come out of Dr. Binyu's work at University of Berkeley, talking about a veridical data science writ large, and then we're looking at a veridical spatial data science. And essentially, again, just mirroring those big important ideas that, this is more than just a data and code sharing endeavor. And we want to emphasize that when we do our teaching, that there's this larger purpose of validation and validity checks to the work that we're doing. And that's really important because that purposeful replication, that purposeful reproduction of past work helps us essentially check and improve not only our research products, but also our larger scientific knowledge and understanding. So again, if we're thinking about key takeaways from this workshop, kind of bringing this all together, we're trying to give you guys a really sort of maybe too much for one workshop, to be honest, but comprehensive approach to how we're thinking about education and pedagogy around reproducibility and replicability in the spatial data sciences, and also even more largely within geography and GI science. And so I think some key messages, just to preview what we're going to talk about as we go throughout the rest of this workshop, is first and foremost, we want to say that teaching reproducibility and replicability is about more than data and code sharing, right? Linking this back to the epistemology of science, or the multiple epistemology of science, and larger set of open science practices that Joe mentioned we covered in last year's workshop, is we think is really important for emphasizing that point and giving, really capturing sort of the excitement of doing reproductions and replications and what they mean to science writ large. The second thing we want to emphasize is that, it's one thing to talk about these things, it's one thing to sort of present them in the abstract, but really attempting reproductions and replications with your students is an extremely rich way to teach GI science concepts, to teach spatial data science, and also just to teach topical knowledge, to be honest. We've done replications and reproductions across a wide range of human geography and even to some extent physical geography studies at this point. So we've covered lots of things in these, and we'll show you how we've done that in the classroom. Similarly here, we think this is a really good way to teach. We think it's pedagogically rich, and we think it really improves both student level outcomes and professor level outcomes. So this is kind of a hard pitch to all those in the room here, that not only are you sort of creating rewards for your students and giving them this challenging and enriching classroom experience, but you're also we've been able to produce a number of publications by doing these reproduction and replication attempts with our students. So if you're thinking about it from sort of the typical academic incentive standpoint, as a professor, getting publications is obviously important, and this is a way to do all these things together at once. And then finally here, we're going to give you guys a big set of different open educational materials, and that's going to work at the curricular level, curricular planning level with the competency rubric I'm about to show you. It's going to work at the classroom level with full classroom resource sets that we've run in different classes, as well as sort of our implementation and approach. And all of these things are openly available. We want you to take them and use them. We want you to reach out to us and help us improve them as we try to sort of integrate this more and more into geographic teaching and spatial data science teaching. So a little bit of time on this slide, but a lot of big takeaways here that I think will reinforce as we go throughout the remainder of this talk. So yeah. Joke bomb, yep. So you get me for a little bit longer. But we wanted to start at the curricular level. So thinking at this kind of top high level of presenting sort of what are the set of competencies that we want people to take away? What skills do we want students to learn when we teach R&R in spatial data science and GI science and geography writ large? And then sort of like, how do we build curriculum around those skills, and then also have different forms of learner assessment? And so what we've been doing to get this ready is building a competency rubric for reproducibility and replicability in geography. And before we dive into our rubric, we have to give a really big, strong nod here to the BEAD network. This is their link, and we really took a lot of inspiration from this competency rubric that they've created for the data sciences, the environmental data sciences writ large. This is a really great resource. They have a really good stuff in there. And essentially what we've tried to do is take a portion of that larger rubric set that is related to reproducibility and tailor it in for the spatial data sciences and GI science to sort of, again, identify what those skills are, link them to an established pedagogical model, and give people a framework from which to build course materials to teach these things or integrate these things into their GI science and spatial data science teaching. So without further ado, let's take a look at that. Okay, so let's first lay down the structure of this reproducibility competency rubric. Essentially what we've done here is, again, mirroring that BEAD network. We have sort of 4 major categories of competency that we want people to develop around reproducibility or doing reproducible research. I will say too, this entire rubric is definitely a work in progress. We're going to release sort of version 1.0 soon, but we definitely want to solicit feedback not only in this workshop, but also afterwards. If people are interested in these things, please engage us. So back to the structure. We have our vertical rows running down here. These are sort of our big different competency areas. And then within those competency areas, we identify specific skills in the first column. And then we have different levels of sort of achievement or learner outcomes running along the remaining columns. So foundational level, basic understandings, second level, something intermediate, and then very advanced, third level skills. And just to give you a sense of what those different skill sets are, within each of these, we have a number of different kind of major skill categories, right? So for instance, in this provenance category, where we want people to learn about recording data provenance, we have the capacity to create data, the capacity to use data, the capacity to, and the skill with using version control, and then also documenting the different versions they do. So within these, there are many different sub-skills that match to these competencies. Yeah. And then the other, oh, this got messed up a little bit. The other idea here is to match those different skills to a pedagogical model. And so we've used kind of the classic Bloom's taxonomy, which got a little bit jumbled here. But essentially, Bloom's taxonomy has 2 different components. So you've got your cognitive processes, which are sort of remembering, understanding, applying, analyzing, evaluating, and creating. And then there's different types of knowledge: factual knowledge, conceptual knowledge, procedural knowledge, and metacognitive knowledge. Essentially, these can work off in pairs. And what we've done is, for each of those skills and levels of achievement in our rubric, match those to a, oh, thanks, Joe. Match those to a specific skill pairing and pedagogical pairing. Yeah. So pop the next one, Joe. Thank you. So for example, here within that provenance category of competency, we have the skill of creating data. One of the outcomes at the kind of foundational level of that is understanding spatial data structures. And then similarly here, we've grafted that learning outcome to the pedagogical levels of Bloom's, that this is an understanding focused level of cognitive process. And it's a conceptual knowledge type. It's understanding that conceptually what these data structures are. So the entire rubric itself has that kind of nesting structure, expanding structure of presenting the skills. And then we've crosswalked those to different pedagogical approaches, or to the pedagogy of Bloom's taxonomy. So here's an example of what a subset of this looks like. So obviously this rubric is quite expansive. Each one of these skills has its own row and different levels of achievement, essentially. So this is a compacted version from our science context column, where we're looking at the evaluating research skill, and that evaluating research skill has a number of 3 foundational achievements, 3 second level or next level achievements, and then 3 third level achievements. So similarly here, if we were to look at the acknowledgement column, which I didn't prepare a condensed version of, we would have different foundational, second level, and third level skills. And then, as I was talking about a second ago, each of those foundational, next level, and second level or third level skills are matched down to Bloom's taxonomy. So for instance here, just to kind of crosswalk through how this works and sort of present it to everyone, essentially here, like if we're thinking about evaluating research, a foundational skill is like a starting point. Is our students able to identify the research question and the type of research study that they're working with and trying to reproduce, right? And this is sort of an analysis application of a conceptual question, right? Can we break down research? And similarly here, we can go across all of these and go through. So for example, a next level skill is not only to identify the type of research, but to evaluate the internal validity of a study, right? So this is kind of higher level on those cognitive processes. We're doing an evaluation task, and we're using the concepts of internal validity and the different components of what makes something internally valid and breaking that down. So to give you a sense of sort of how this works. And then kind of at the top level of that, we have something not only would be identifying validity concerns and assessing them, we'd actually be designing solutions or alternative pathways to examine those validity concerns and potentially address them in the study that we're attempting to reproduce. So that's a much higher cognitive level task. We're creating something new, creating a design, and we're trying to implement it. And it's kind of a metacognitive level, this much higher evaluation planning level. And it also has some procedural overlaps there as well. So you can see even in this brief presentation, there's a lot of things going on here. These things can probably be categorized in different ways. But just to kind of start this conversation and give people a starting point for how these things fit together, this is a good look. And the last thing I'll say about this slide is this science context skill, maybe people wouldn't think in a normal sort of reproducibility rubric, but this is also where we're trying to take that more expansive view and not only focus on data and code sharing aspects, but really contextualizing why we do a reproduction attempt or a replication attempt, and sort of what are the important skills in setting up those attempts or positioning them within the larger spatial data science or scientific sort of discourse. So here's one example of one of our skills within one of our competency areas in this rubric. So just to give you one more example to kind of bring home this point, you can kind of see already how it works, but within the provenance competency, we want people to develop this broad competency of generating and using and evaluating provenance. Within here, for instance, we've got the skill of version control. And again, you can see the unfolding of the foundational level skills, the foundational levels of achievement, the second levels of achievement, and the third levels of achievement. And here again, just a basic one would be just understanding what version control is, and also being able to create sort of a local version of version control on your own computer, just these very foundational start points. And again, that sort of emphasizes this understanding level of Bloom's taxonomy of like factually what a version control is. And then if you're creating a local one, you're applying that understanding, and it's a procedural type of knowledge that you're executing, implementing. And then similarly here, these can expand out across to the second level, the third level. And at the third level, again, you're at the high level here, looking at creating a version control process, not just using a version control software, but actually creating an entire process, particularly one on the T2 here that you're going to use collaboratively with many different researchers. That's going to involve branching, workflows, pull requests, just checking and evaluating work, and then being able to bounce forwards and backwards in those versions as necessary. So moving much higher up on the kind of cognitive process level again. So I think those two rubric subsets here kind of give you a flavor of how this works. It's a little bit too big to put the entire rubric out for everyone to see in this format virtually, but we're going to share this entire thing soon, and we'd love if people took a look at it, adopted it, and gave us feedback. But I think, having presented that structure and given you a couple of pieces of flavor, I think we did want to open up for a few minutes of questions, take a break and discuss this rubric, and we can always bounce back to these other ones if need be. We have a few more prepared to discuss. So with that, I will stop and hand it to Drew to pull out any questions that we've seen in the chat, and we can respond to those before moving into our next section. So, Drew, any questions for us?
Yes. How do you make sure you measure the correct type of success in education, i.e. in project-based education setting, learning outcomes? How much a person has learned is probably more important than the quality or level of the project results.
Joe, you want to take a crack, or you would like me to go?
Sure. Yeah, it's a really good question, especially when you're talking about trying to reproduce prior research. And in this context, you often simply do not know when you try to start reproducing a paper how challenging it is ultimately going to prove to be, and or feasible for that matter. So you kind of have to be flexible in terms of recalibrating expectations throughout an attempt, especially if it's limited to the time during a course inside of a semester. So that's one point, is like to that question, is that the expectations need to be flexible as you go, depending on the challenges that you encounter. And along those lines, so you can reset the expectations, basically. I think you always sort of want to look for equality, but you might want to you kind of have to be adaptable and actively engaged with the students to see how they're engaging with the material, so that you can reset the expectations to something that they can deliver with high quality. So I've definitely had reproduction studies that ended up, spanning multiple semesters. So, for example, a climate vulnerability model with 3 major components or subcomponents to it. We started doing it and then realized it was actually going to be quite a bit more difficult to acquire the data and wrangle the data into that final model. So we decided to do 1/3 of the model early on and just kind of focus on a subcomponent of the research project rather than trying to bite off the whole thing. But also, in presenting this competency rubric, we're really trying to reemphasize, much like Bernd is suggesting by the question, trying to shift the emphasis to competencies and skills overall, and that is competencies for doing research and engaging with the scientific community, as opposed to particular competencies, for example, in knowing how to use a particular set of tools in ArcGIS or a particular set of functions in R or Python. Sort of shifting away from that detailed, lengthy, list of particular techniques or data sources that you might traditionally organize a course around, to these more almost softer skills in a sense, but they're also technical, but skills for doing the research and learning from it.
Yeah, that last point, Joe, is the one that I was going to emphasize too. I think this is, again, a really good question. And, it actually gets to the point of what we're going to show in our implementation, which is this next section that's coming up. But essentially what I just wanted to reinforce there is that what we have found in attempting reproductions and replications with students is that doing that really teaches them the sort of how to do research and how to deconstruct and tackle a problem, right? And so a lot of the things that they actually learn are hard for us to capture in a rubric, because they sort of learn all these kind of higher level sort of like teamwork, organization, holding each other responsible kind of things that are really important outcomes that aren't necessarily directly captured in the rubric, but we think are really essential for being good scientists, being good citizens, a whole larger range of things. I think with the rubric here, what we've been trying to do is sort of systematize some skills and practices from open science that align with things like the 5-star guide for reproducibility that John Wilson and others published a few years ago, the Agile reproducibility guidelines for their conference paper reviews, where we're trying to move the field towards having these research products, having these work products essentially that meet these reproducibility, reproducibility standards. And in doing that also, where we're obviously moving also the way in which we work more towards this open and essentially checkable type of science, essentially. So I think just reinforcing what Joe said, the competency rubric is there sort of as like to help you plan, right? We wouldn't say you have to do the entire thing, but if you're trying to identify like what are some important aspects of this, again, we've sourced the things that are in the rubric from not only that BEAD initial initiative, but also reviewing like those 5-star guides, the guides from Agile, a number of other publications about what it takes to be reproducible, and try to fold those skills in so we can sort of give a set of signposts for things you might try to integrate into your courses and your course planning. So again, this is at this high level, course planning level, curricular level, but yeah, it doesn't cover everything, of course.
Another monkey wrench in that question is how do you do it? How do you actually do the assessment? So for me, it's meant shifting towards a lot more self-assessment from students, cognitive reflection on their part, doing a little bit of writing about how, what they're getting out of the course, and how they feel about the work that they've been doing, and setting some of their own goals appropriate to the skill level that they came into the course with. And ultimately, I lean on those self-assessments pretty heavily for a final grade. I wish I could not grade at all in these kinds of classes, kind of adopt the ungrading approach. But I lean on those self-assessments and ultimately kind of looking at their materials in terms of how reproducible what they have done is. Like, are they really implementing these practices, as opposed to evaluating like how nice of a regression model they came up with. It's more about how reproducible they're communicating their work, how reproducibly they are communicating their work.
Yeah, and I can say too, Joe, I know you've had this experience at the undergraduate level, but me primarily working at the graduate level, a lot of this answer is that the work isn't done, and it often spills over. So I've worked with graduate students several beyond the end of a class where we attempted a reproduction or replication, and it's spilled over into preparing a larger report, or it's turned into some other kind of more elaboration on the project. So again, it's not that everything is contained entirely in the course or entirely in the rubric, but we're actually creating these kind of like ongoing investigations that students continue to benefit from on through the future. I think this is probably a good time too to pivot over to actually maybe answering this question in even further depth by showing you how we actually implement this in the classroom. So I'll hand it to Joe to kind of walk us through that, and we'll have some more question time again at the end. So Joe, back to you.
Yeah, for an overall introduction to how we've actually implemented this, let's start with our geographic and situational context. We have completed reproduction studies in advanced undergraduate open GI science courses at Middlebury, in graduate spatial statistics and spatial analysis courses at the University of Arizona and the University of California, Santa Barbara, and in independent research and thesis projects, summer research internships, and as the focus of special reading or study groups focused on learning new methods. For example, Peter led one on spatial Bayesian statistics. A group of graduate students wanted to learn that new method, and they approached learning that new method by doing a reproduction and replication study together. In terms of our approach or our process, each reproduction attempt follows an archetypical process starting with a close reading and dissection of the original study. We then develop an analysis plan for the reproduction attempt and optionally register that plan on an open science platform. At the fourth and fifth steps, we attempt to execute the reproduction study plan while comparing our results with the original study. And then finally, we share the results in reports, reproduction study websites, and even peer-reviewed manuscripts. And as ambitious as this may sound, we've proven that it actually can work, and you also do not need to start from scratch because we've got a wealth of materials available to you. And that toolbox includes 10 reproduction studies and counting that have been completed and published, a didactic template research compendium for organizing the work involved in creating a reproducible study or a reproduction study that in and of itself is reproducible. This includes a template analysis plan that is specialized and suited for spatial research. And we've got GitHub-based course websites that have links to prior student work, lists of studies for possible reproduction, and a pedagogical framework for reproduction studies as project-based learning, which Andrew will introduce.
Thank you, Joe. So when we began to think about formally implementing these ideas in the classroom, we knew that we needed to be grounded in strong pedagogical theory and practice. And the natural match for that was going to project-based learning. Now, most of the time people think of project-based learning as just doing a project, but as you can see here, there are a number of different components for project-based learning. In fact, the model that we're using right now has 7 of them. It goes from the challenging problem, sustained inquiry, authenticity, student voice and choice, critique and revision, reflection, and public product. And we highlighted some of these just to point out that a lot of times when you, in a typical GIS classroom, when we're doing something like a lab lecture model, or we're doing a student-based project where they design their own project, we don't always meet all of the criteria, the components for project-based learning. And so when we're doing something like a reproduction, here we are trying to make sure that we implement each of these individual components. The middle column then gives an interpretation of what we feel each of these components means. So a challenging problem, well, we want to make sure that the question that the students are trying to answer are at the appropriate skill level for what they're trying to do. Sustained inquiry, this is, again, an extension of a process of questioning. Authenticity, we're grounding that in real world context. Student voice and choice, making sure that the students are involved not only in the decision making, but then the implementation of what is going to happen with the project. Critique and revision, we want to make sure that this is a continual process where there's receiving and giving and applying then feedback, not only from the instructor, but also from the peers. And then with reflection, again, a continuous learning and looking back on the effectiveness of the decisions that are being made. And then the last part, which is often missed, is then the work being shared beyond the classroom. In the third column, what we decided to do is then give an example where we take then these ideas of reproductions and replications in the classroom and then link it to each of these. And this is just one example for each of these because there's a lot of words, and we're currently writing a paper at this point in time, and we're trying to, link all of these things together. But you can see here that, we're critically evaluating, with the challenging problem, we're critically evaluating the design and execution of prior studies. So we're getting them involved then in the actual literature, which takes us to the sustained inquiry, where you have an iterative evaluation of the work, engagement with peer reviewed empirical research, grounding it again in the literature to have that authenticity, and then making sure that students contribute to the project selection, and then they are the ones leading the designs and revision. When we get to like something like critique and revision, there's a lot of communication going on, student to student, student to instructor, and even then student to the larger GIS community. When they reflect, they look back and go, oh, okay, what were the design decisions that we made? How effective were they? What were the analysis? Did they turn out appropriately? Did we get something completely different? And where were the unexpected challenges? Where are the places where, if we're going to then redo this kind of study, that we can make it more replicability friendly? And then finally, the public product, where there is actual sharing of this material, something like what we're trying to do here with this workshop. Now, before we get into the actual implementation of R&R in the classroom, the one thing we wanted to recognize, it is a lot. There are a lot of components, there's a lot of process, and it all is very new. And you don't necessarily have to jump in and do everything all at once. And so we want to make sure that you start to look not only at the broad picture of what's happening, but maybe focus in on one or two component parts that you can then say, oh, I can take that activity and turn it into something in my classroom. And even if you just do one part of this, it is extremely rewarding for the students. I don't have the luxury of being able to have classrooms like and courses like Joe and Peter do. So I have to take parts of this and then get them to think about the papers and do some of the implementation of the different parts of a replication that Joe's going to go through and talk about now.
Thanks, Andrew. It's a good opportunity to link back to the competencies too. When you adopt this project-based learning model, you de-emphasize a long syllabus of particular concepts or methods in a course, and you re-emphasize the competencies, right? And in doing so, you're kind of teaching students how to be really good self-learners. You're enhancing their confidence and their self-efficacy to participate in the scientific community. And you're giving them all those skills to understand comprehensively what a research project is all about and how to implement it on your own, right? So I'm going to walk through an example of one particular reproduction study that we've worked on for a couple of semesters of my open GI science course, and for which a student has also spent some time on as a summer research assistantship. And this study was by Jay Chakraborty in 2021, and it's an analysis of disability and COVID-19. So this was early in the pandemic. The pandemic hadn't diffused even to the entire country yet. Places like Vermont and upstate New York hadn't really seen much incidence yet of the disease. And Jay was interested in sort of a preliminary exploratory analysis of whether places with large numbers of folks or percentages of folks with disabilities were seeing disproportionate impacts of COVID-19 in terms of the incidence rate. So the first step in doing one of these reproduction studies is something that you could peel off and do in any methods class, really, as sort of a one semester or as a one seminar or one lecture activity, where we deconstruct the published study, discussing the overall study design and its hypothesis or hypotheses, and highlighting all the clues that we can find in the manuscript as to the data sources shown in cyan here, the methodology, which is highlighted in pink, and any intermediary or final results kind of shown in yellow. And this also kind of starts to highlight the fact that our scientific publications that we write and get through the peer-reviewed process never contain all of the details that someone would need in order to reproduce that study without any ambiguities. There's too many details and too many decisions that we make as researchers in our study designs and execution to fit inside the package of a peer-reviewed manuscript without losing some kind of information, right? So this is always going to be a little bit challenging. But here you can see this was a short article and really densely packed with important information. Jay was extremely efficient with his words in this one. And so once we have sort of spent time dissecting the manuscript, then we try to draw a workflow diagram that looks much like a visual programming graphic workflow that you would use in desktop GIS software that highlights or basically illustrates the entire study design, and also highlights any of those moments using the same color coding here, yellow for intermediary and final results. Highlights anything or any of the products or tables or statistics embedded in the text or in the figures of the manuscript that you can use to check your results as you go along when you're trying to implement the reproduction study. Or if you're starting to find it to be more challenging than you anticipated, you can peel off some of those sub-goals or intermediary results as a sub-goal for students to focus on rather than doing the entire thing in one semester. And just some methodological notes about this particular study. Jay was working at the county level, and he essentially wanted to use generalized estimating equations to control for spatial autocorrelation in his estimation of whether there was a pattern or a correlation between disability rates and COVID-19 incidence rates at the county level in the United States. And so generalized estimating equations need you to define a clustering criteria, and they look for autocorrelation found within those clusters that are predefined when you run that method. And so to create the clusters, what JU did was combined information about the state that a county was in with information about whether it was a COVID-19 hotspot according to a spatial scan statistic. And so that's the kind of study design that we're looking at. And as a first step of implementing that research or that replication study, we would start with a research compendium template. And so my colleagues in data science at other liberal arts colleges, or teaching statistics even at other liberal arts colleges, have found using a template extremely useful for teaching overall, because students are organized with their work in and of themselves, but then when they need help, or you need to evaluate them, or you need to consult with them, they've all organized their work in exactly the same way. So it drastically reduces the transaction costs of trying to figure out what's what within their work in terms of where their code is, where their data is, what their plan is, et cetera, et cetera. So we highly recommend kind of using this consistent directory structure. It's an easy win, and it makes for much easier teaching and advising of projects, especially if you've got a lot of independent thesis projects or master's level projects or something like that. We also do implement it in GitHub using version control so that there's a history of all the changes that have been made to the project over time. And we have templates for metadata embedded in that directory structure. So overall study metadata is implemented according to the Dublin Core standards so that it can be ported over to a repository or an archive, a digital archive. And the data sources, we use the ISO geospatial data standards to give a template for documenting your data sources and recording metadata on those. And so at this step, you're really just kind of filling out metadata in README files and starting to save your data in a raw data folder, but not yet looking at that data. You shouldn't be manipulating the data before you have completed this next step, which is to document an analysis plan for your reproduction study or your original study. So this addresses questionable research practices in science where people p-hack or sort of change their study design, adapt their study design as they're going to get that significant p-value results that they are expected to get for publication. By recording your analysis plan ahead of time, you kind of set in stone one version of the study that you intend to implement, and then you have to be transparent about any choices that you make to change that study design thereafter. Again, my colleagues that teach data science at other liberal arts colleges really appreciate this analysis plan stage because it requires students to think very intentionally about their research question and define a reasonable methodology for answering that question before they start mucking around with data and analysis programs. So when they do start actually doing the work, it's much more intentional and they have a much better idea of what they're doing. And you've also had a step before going into the data where you can get to evaluate how good their research questions are and how well their proposed methodology suit the research questions. So we actually have a template for this that is suited for the geospatial sciences. And we've provided it in both regular Markdown format, but we've also created a Jupyter Notebook version and an R Markdown version so that you can write your analysis plan into a computational notebook without yet writing the code to make it work. And so then you can, if you want to be completely open about it, you can render a PDF of that and register it on an open science platform like OSF. The next step then is to start trying to make it work, right? And so the beautiful thing about writing your plan in a computational notebook is that after each paragraph of the plan, you can put code blocks in there to make that part of the study work. So on the right-hand side, I'm just kind of showing in my data section, I wrote about the fact that the study is going to use American Community Survey data. And then I put a code block down there below to use the tidy census package to query that data from the census. So there's a lot of synergy then. It's very legible code. You're sort of putting the code into the plan to make the plan function. right? So you start adding code blocks to your plan. You check your results as you go, and you also you should teach students how to write code to compare the original results to the results that you're getting in your reproduction or your replication attempt. And those inevitably lead to inconsistencies or ambiguities, things you didn't anticipate when you wrote your analysis plan or that came out differently than the original study reported. We call those the unplanned deviations. And so just some examples from Jay Chakraborty's study. If we think of an ideal workflow going from start to end, we generate our descriptive statistics, we calculate our correlations, we find those spatial clusters, and then we do our generalized estimating equations in a straight line. That rarely ever happens. And I sort of illustrated it like this to indicate that what you find yourself in often is these little eddies of like a little inconsistency in the descriptive stats where you weren't sure which subject table to grab the data from in the ACS survey, for example. And you have to kind of iterate through that step a little bit to find exactly the right data table to match the original research. In the correlations on this one, we found that a couple of 5 data rows out of all of the counties in the United States were somehow translated or swapped. The data was swapped in them from probably translation of the data from one data platform into another. And so the correlation was off by like the 1,000th point, but that was actually caused by a little tiny inconsistency in the data that we were able to fix. And then we found major differences in terms of computational environments for implementing a spatial scan statistic for identifying significant clusters of COVID-19 incidents. The map on the right shows those differences. The areas of agreement are tan on that map, and the red and the purple both show areas where either one software implementation of a spatial scan statistic found that cluster or the other did. And so this leads to potentially major difference in the outcome of this study, right? And it's nothing that the author necessarily did incorrect, but it's a major implementation difference between a couple of different software packages for calculating a spatial scan statistic. So that almost leads us into a channel braiding situation for our flow of the reproduction study, where we may have multiple branches that we want to see out to the conclusion, and then be able to compare the results to see how important the programming decisions were in the implementation of the spatial scan statistics for the outcome. Right. And so that brings us to the end, and we'll need to write new code again that's different from the original study to compare the results. We have probably at a minimum of 2 different result sets, one from the original study and one from the reproduction attempt. But in our reproduction study, we may, as I was mentioning, kind of carry multiple threads of analysis out all the way through to the end in order to do a sort of sensitivity analysis to see how important different decisions or computational environments were for the results. So in this particular case, we learned how to do dot whisker plots and basically put 5 different series of 5 different scenarios of the study on the same graph and compare how much of a difference those may have made, right? And so as we're doing this reproduction study, you're probably getting a sense that students are building skills here. And they're not the skills we normally emphasize when we're teaching spatial analysis or geographic information systems or spatial data science. They're skills more oriented towards like dealing with uncertainty, dealing with error, and sort of being able to write the code that will allow you to sort of synthesize and quantify how important errors and subjective decisions are in your research flow. And they're also explicitly kind of moving students away from the idea that there's one perfect solution to a study, but there actually may be many possible working paths that researchers could take to answer a given research question. And then you can follow those different paths and compare the results. And so finally, once you've sort of made all that code work, you develop an analysis report. Ideally, you develop all of the table design and figure design in code itself so that the study is fully computational and so that you can render one final report using the computational notebook. And then you go into a discussion in the discussion section of the unplanned deviations, why they occurred, and how important they were based on the differences that they made in the final results. And write a conclusion section that basically kind of reflects on the contributions that the original study made to the literature and any additional information or insight in terms of the validity or importance of that original study that you have discovered through the reproduction attempt, as well as ideas for future research that you probably encountered along the way. And that final analysis report can be registered to PDF or to HTML. In my courses, I have them rendered to HTML so that I can add them to a personal website that they develop on GitHub. If you render to PDF, then you can easily register that on an open science platform like OSF. And so we've done this with 11 studies and counting. We've learned how to do this a little bit better over time. So the ones we started earlier are a little bit less complete or up to higher standards of open science practice than the ones that we started later on. But as you can see, we've done it at a variety of different levels, undergraduate and graduate. We've made all of the work recorded on GitHub, and to varying degrees, we've also registered that work in terms of compendia, pre-registered reports, preprints, and post-analysis reports on Open Science Foundation, OSF. And several of them have already led to peer-reviewed publications or things that are in the review process right now.
Yeah, can I add one thing to this one, Joe?
Yeah.
Yeah, so a couple of additional thoughts on this list of papers here. We show this for a couple of reasons beyond what Joe said. Obviously, we're proud of the work we've done. It's all very open and accessible, but we do really want to reinforce that, we also see these studies as a resource for all of you that might want to do this in your classroom. So, implementing one of these from scratch certainly does take some time and take some effort, and we don't want to minimize that. But we thought that one way that might be helpful for people in the audience is to literally just take these studies and further elaborate them, or sort of redo them, or redo portions of them with your students in your classroom. So one of the things that we're working on, we have many goals with this project, of course, but one of the things we're working on is sort of properly indexing all of these studies together, not only with links for where all of these resources are, but also emphasizing sort of which GI science skills, which statistical methods are covered in each of these courses. So if you were teaching, for instance, a course like Joe talked about from the Chakraborty study, that is you trying to use regression analysis, maybe some more advanced forms of regression analysis, that may be a good study to work from and include into your class in some way. And you can use all of our code, all of our diagrams are there, all the things that Joe showed you are very much available online. And similarly, if you wanted to do something that was more Bayesian focused, the DiMaggio study here is an implementation of a Poisson model in a Bayesian framework. Again, that one was also examining COVID, but the Spielman one is about the SOVI index and the effects of scale and geographic extent. So there's lots of different things going on here, but we really see this as an open resource. We really encourage people to take up and use however they wish and however they like. And additionally, too, as Drew mentioned before, we're trying to get our acts together and sort of write up the encompassing paper that sort of lays out all the things that we've presented to you guys in a written format. So it's a little bit easier to always reference back to and assess. But in addition, in that paper, one of the things that we've prepared is an appendix of additional studies that we think would be interesting targets for reproduction or replication attempts. And so those we have not done yet, but we think would be sort of interesting for teaching. Maybe we have one selected for introducing remote sensing. We have one selected for introducing spatial clustering statistics, things like this. So we are producing a whole bunch of resources behind the scenes that these are already available. And Joe's going to show you the link to that in a second, but there's a bunch of other things that we're developing as well. So I just wanted to sort of reemphasize that point on top of what you said, Joe. So thanks.
Yeah, and I think once you start to get a critical mass of these together, the pedagogical opportunities expand drastically, right? And just going back to Jay Chakraborty's example, his study was fundamentally about correlation between disability rates and COVID-19 rates. And the journal that he submitted to probably had a limitation on the numbers of figures that you could include. It certainly had a very tight limitation on the word count, which limited what he could express in the peer-reviewed article. But when you have a complete computational notebook and registered report, there's unlimited space for all of the details, right? And so you can get a much better understanding of that original research project when you start working with the code as well. And the example I wanted to give was, suppose you're teaching a class that's just doing some basic data visualization in R or Python. There were plenty of opportunities in this study simply to make additional figures and graphs so that students could have a better understanding of what the study was doing by mapping things like the disability rate over counties in addition to the COVID-19 rate. The fundamental question of the study was, how are those things correlated? But in the constraints of the peer review publication, you only get to see one of the maps, not both, right? So when you start to find those opportunities, they're very discrete contributions that a class, even at a very introductory level, can make to improving the overall study or the accessibility and understandability of that overall study.
And if I could, Joe, sorry, could you
Yeah.
go back to the Chakraborty? Because
Which one?
The first one where you're doing the highlighting. Yeah. Next one. Perfect. I just want to point out, when I mentioned before about taking pieces away from this, I don't, like I mentioned before, I don't have the capacity to do a whole class to do the entirety of a replication. But doing something like this to then have students identify each of these components and have them engage in the literature in a very meaningful way where you have a little bit of control on it and you can have a discussion about it is extremely, extremely important. And it really gets them to think about these things in different ways beyond just kind of a lecture communication between the instructor and the student. And I think it's great too that the point that Joe made, you have then the ability to play with these things and show other kind of maps, things that they can do that oh, this is a part that leads to this, that leads to this, that leads to this. I think these things are extremely rewarding that you can just implement into the classroom relatively easily, even if you're not at the point where you can do an entire replication. Thank you.
Yeah, and then you're building science literacy, right?
Yes.
As opposed to how to do a geographically weighted regression. But then students can pick up a paper that has a really good example of a geographically weighted regression and use that paper and its materials to kind of work through it on their own. That's the idea, right? Which, if you need a geographically weighted regression project for students to do, have them pick up this paper and switch it from generalized estimating equations to a GWR, see how much of a difference it makes to switch the method. So I do want to highlight that we have a workshop website. Sort of maybe a hallmark of success is that you lose track of how much you've done. And I think Peter and I were both, the three of us were in that situation yesterday, oh my gosh, how do we get all this stuff down so that people can get it? So I think we got the most important things on this website already. And we certainly have more publications than this by now. We've had a very successful year since we initially designed this slide. But I'll just maybe click on that link so folks can navigate to it, and highlight that the splash page is sort of old now because it was the workshop description, but this workshop resources page is where you'll get links to all the really good stuff. We have an overall GitHub organization where we keep most of our GitHub repositories. So you can find all of our repositories and follow us there. And we have an OSF project where we create projects that link to those GitHub repositories so that we get DOIs for them. And that's where we can register our pre-analysis plans, our post-analysis reports, and our preprints. And so those are on there. And then this next heading has resources that were directly shown in the workshop that you might want to try to use in your courses. Our template is here. That's a GitHub template. If you have used GitHub before and have an account, starting to use this is as easy as the green use this template button in the top right-hand corner. That'll make your own repository that uses this structure, and you can just get rolling with that. There's fairly explanatory README documents. And one of the things that we should always be writing but haven't taken the time to complete is a manual for practicing open science while using that template. I hope that that'll be done in the next year or so. I did put a copy of the competencies matrix that Peter was talking about here. That's an Excel sheet that you can take a look at on your own. We would love to hear your feedback on that. It is draft mode though. And then the Chakraborty study that I presented, we have the GitHub compendium OSF project, the pre-registration and the analysis report linked there. And finally, the course that I taught at the undergraduate level, Open GIScience. I've done all of the work for that course on GitHub, and all of the students' work is also public on GitHub. If you scroll down to the bottom, you can see how they are doing with that. They've got blog. Each of them has a blog that links to their GitHub repositories and their reports for the studies. I think we're at noon right now, and in our timeline, we planned on opening up for Q&A there, but maybe I'll give Peter a chance to return to the key ideas to reemphasize those and then open it up for Q&A.
Yeah, so just reemphasizing, Joe, if you guys have questions, because there's a lot of material here, please just write them in the chat and we're happy to discuss them or break things down. We can also navigate further to those resources Joe was already showing and drill down on those. Yeah, we're very happy to talk about anything. I think I'm getting a message here. Yeah, if you just give us the questions, we're happy to answer them. But just to kind of, again, return to those wrap-up points, as Joe was saying, the big things here is that we're kind of extolling everyone, like, please, teach reproducibility and replicability as more than just data and code sharing, right? It's part of this larger scientific process. It has this broader epistemological function that we think is really important to emphasize when you teach these things, because it turns reproducibility from being sort of this procedural task to one of sort of exploration and discovery. And we have found that that is like super important for engaging students, but also sort of important for ourselves to remember that, this isn't the go and get your root canal done when you're finishing your project. It's brush your teeth every day and also enjoy the process of having good oral health, right? Is sort of the analogy here in some ways. And then similarly here too, it's not just, looking at these things, it's actually attempting this with your students, right? Doing these things with your students, attempting to reproduce a study or even a small portion of a study, or even just breaking it down, like Drew said in the beginning, really does emphasize to students that there's more to this than data and code sharing. And I think also sort of we have found sort of captures their imagination with the scientific method, because quite honestly, they're part of the scientific progress, right? When they do a reproduction attempt, they're doing some form of internal validity check of a published paper that a bunch of us have probably reviewed and identified as something that's interesting and important to publish in theory, right? That's one of the things that peer review is supposed to do. So they feel part of the scientific process, part of, GIScience, spatial data science in a very direct way that we find is very empowering. So we really stress that people, hope that people will pick this up and try to do some of these things with their students. Obviously, that's a difficult process, but we've tried to create a lot of educational materials that we've openly shared with you guys to make that easier to do. And I would say too, we are very happy to collaborate and work on these reproduction attempts, replication attempts with you and with your students. So we've made the resources available, but we ourselves are also available to help try to tailor these materials to your courses or work on reproduction replication attempts with you. Again, we've had some success publishing a number of these already. We've got a number of them that are also in various states of completion, and some are very much ready to be sent out to journals. Others are getting wrapped up still, but we've kind of done this a bunch of times and gone through the hurdles, the trials and tribulations. So if you are trying to do these things, please reach out to us, and we are very happy to help with that process. So yeah, I will. Sorry, go ahead, Drew.
I was sorry, I don't mean to interrupt you, but let's get to some of the questions, because
that's what I was just going to ask.
Actually, what you just talked about before you talked about a call for collaboration was an emphasis of one of the questions, and I think it's a really good point to go back to. And the question is, how do you get students to understand the benefits of working reproducibility and not see this process, as often happens, as extra work? Is there a tangible reward for them?
This is sort of like the turtle and the hare story, in a sense, right? Like this slows things down at the front end of doing a project. And so you've got to acknowledge that, like, there's some new skills to learn. You wait to get into the data and analysis for much longer than you normally would, or than folks are used to. So you're slowing down the beginning of a lab or an analysis or a research project. The rewards are on the tail end of that, right? When you realize that your formula for calculating catchment area at the beginning of a floating catchment analysis was missing a parameter, and this is a real story from right before the fall semester started. And that affects every single figure and calculation in an entire study. And after realizing that, you can edit the code and rerun the study and have a new paper in the matter of a couple of hours, as opposed to spending a couple of months trying to recreate all of that stuff, right? The rewards are more on the back. It's a delayed reward, right? But the reward is there. That's one of the main points that I would say. The other reward is, like, we're breaking down the barriers between the classroom and the research lab, right? We're learning methods where we can get our hands directly on cutting edge research, the stuff that's been published just now or just last year, and learn how that research is working. And I don't think that's a promise that most classes can make, but we're kind of sharing the real challenges of doing that, of getting into the cutting edge contemporary research. Those are two thoughts that come to mind. Peter, and Drew, do you have more?
Yeah, I was going to add to that. Again, I do think framing this all as sort of a collective knowledge generation process, and sort of being involved directly in the creation of new science and new knowledge, is very exciting to students. And so framing the entire approach as, this is an endeavor of discovery, right? And the idea is not only to discover it for yourselves, but to also create something that other people can build upon and check. And I think students, in our experience, have really engaged with that process. And I think also, too, the way in which we present it is important. And this is more elaborated in the draft paper that we'll be putting out soon as a preprint. But it's really kind of like Joe's suggesting, we go back and forth between not only lab, lecture, and breaking down that barrier, but we also do a lot of diverging, converging, where we have the students do something individually, like deconstruct, like take a first pass at deconstructing it, and then we come together and sort of have this kind of actually quite fun event where we critique the paper collectively and sort of like build out the workflow. Or when people encounter a coding problem or some sort of things they get stuck on, we get to come together and solve that collectively. And that process of working together, I think, is quite enjoyable for students. So there is like an extra work component to it, but there's also a collective working component to the way that we've done these that I think gets past that extra barrier or burden, because people feel like they're part of a team, they feel like they're part of a group, and also a larger endeavor that we really find quite motivating for the students, that I think helps answer this question too.
Yeah, we also shouldn't forget that one of Peter's PhD students also is a analytical consultant for Mathematica, and brings up the point that in government work or in any government agency doing for the government, reproducibility standards are increasingly expected of those career paths and the work that's done in those career paths. So whether you like it or not, it's also skills that will look good on your CV and be directly applicable to a career and to working in a team, quite frankly.
So the next question is from Ivan. If most university classes move to the PBL format, what is the benefit going to university versus self-learning and doing projects in an internship?
I think, well, Peter's converging. You don't get to have the convergence step or the collaborative step if you're doing it by yourself. It also, there's a lot of expertise that we still need to bring to the table as instructors when we're doing this. Undergraduate students don't have a clue what a generalized estimating equation is. They need your help to understand the methods in the papers, to look for good teaching vignettes, to walk them through the finer details of the methodologies that are being applied in the research. That is difficult to do on one's own. That's two answers.
Yeah, I think too, similar to that, Joe, the idea here is that, one of the, at least in theory, right, reasons that, we have become professors is because we have some level of expertise in these particular topic areas. And so, we're sort of doing a filtering curation task that certainly we do imperfectly, but we try to identify what we think are important competencies and skills to learn, and then sort of provide these experience by which to learn them. So yeah, project-based learning it's not just doing a project, right? It's using the project to hit on and touch a lot of different important skills and competencies. And of course, we can't cover all of them, and we may not pick the perfect set for every different outcome that a student may want. But hopefully we're sort of coming up with an experience that is teaching important fundamentals, both on the GI science side, both on the project side. And we're using project-based learning as an avenue for teaching those things. And then ideally, in our approach, trying to link those back to a competency rubric that systematically is covering a lot of these important skills, not only from an academic perspective and a science perspective, but also from a professional perspective if you're looking for work. And, ideally, once you've become good at that format yourself, you could go and create those experiences for yourself as well. And we're trying to make it as open as possible so people can do that. But, I guess we like to think that we have something to add to that process. And that's, I think, the answer to that one. Drew, one more question because we're almost out of time, I think.
Yes, we have one more question. And it's very similar in its content. With PBL format learning, though the benefits can be seen, but would there not be students who would opt out of coming to class since everything is just project-based and they could do it at home?
I would like to take that one. I can't understate how authentic of a challenge it is to complete one of these reproduction studies. And as sharp as the students at Middlebury College are, none of them have taken that route of kind of going on their own, even though that happens in other classes. The authenticity of the challenge and the need for collaboration and the need for guidance keeps everyone highly engaged when you're doing this. I think that's what I'd say for that.
Yeah, I've had the exact same experience at the graduate level. Like oftentimes the, lecture sessions and the lab sessions just kind of break out into these spontaneous problem-solving groups where the graduate students are working together on things. And certainly they also do that behind the scenes using things like the GitHub issues feature where they can trade back and forth, so they can do it remotely. But really those like coming together sessions where they're in person in that very media-rich environment helps them troubleshoot problems in this very direct way. So again, I think the project-based learning as an authentic challenge has this actual nice balance between the virtual remote experience of working on issues sequentially and organizing work when you're in different places, but then also having these come together times to sort of like sort out the more challenging problems that are not only technical, but are actually often conceptual. And really those conceptual problems are difficult to sort out, even over email or text exchange. You really need that face-to-face, very rich environment where you can like talk through these problems and figure them out. And oftentimes, again, a lot of the unintended changes that we have to make come up because something was vague in the original research paper and we had to go around and twist it. or we had to go around and figure it out essentially. And that really works best in those rich formats. And with that, I think we are out of time. But I guess just as we close, I'd reemphasize, please, please, please reach out to us through our websites, through our emails. We're very happy to engage with you and work on this, help you bring this into your own classrooms. Or if you want to just attempt reproductions and replications, we're more than happy to dive into that with you as well. So Joe, any last words from you?
No, thanks for everyone's attention and interest in the topic, and would love to hear more.
Yeah.
Great.
Thanks so much, everyone.
Thank you, everybody.
Thanks, everybody. All right. Last final words from me, just thanking the session organizers. That was fantastic. We have a 60-minute break now for lunch or dinner or whatever interests you. And then we'll be back at 1:15 Eastern time or 7:15 Central European time for our last thematic session, Spatial Data Insights in Urban Accessibility. And we look forward to seeing you then. Thank you.
Thanks, Grant.
Thanks.